Welcome to Math 106, Chapter 5.2, where we talk about compound interest. So this is where kind of the financial aspect of what we've been learning comes into play with our value of E and your ideas and derivatives of that exponential function. So compound continuous or continuous compounding. If the number of compound periods per year is increased indefinitely. So how compounding works is that this is your interest that you've earned in that account that then just rolls over into your account. And so it is inflating your value, it's inflating your account, and it's just happening over a set period of time. So, or a set number of times per period. So if we said, hey, we're going to be compounding once a year, so that investment kind of rolls over on itself just once. Or if it's semi-annually, it's twice a year. Or if it's monthly, it's 12 times a year. Whereas indefinitely, right, is continuously. So it just goes on compounding on itself. So if your savings account was compounded continuously, it will grow exponentially like the fruit flies. Therefore, we use the same formula as before, but alter some of your variables. So you might see something like this, which you might have also seen in science class or maybe your business classes where they kind of refer to this as PERT. That's because, let's take this part away. It kind of looks like the word PERT. This is just talking about these financial terms, whereas A of T, this is your final value of the account or what's in it at the end. So anything that suggests, hey, it's going to be worth this much in the future, or this is your future value, anything that will have the context of happening later. Whereas P naught, we know to be the initial amount. Initial amount, initial value, your present value. We could also say that this is your principal, your starting value, anything that suggests you have this value right here and right now. We know E is your value E. R is your rate. And T is your time. So if, in example one, $1,000 is invested at 5% interest compounded continuously. So they tell us that it's compounded continuously, so we get to use your above formula. We're going to talk about some of the other compounding aspects, equations later. But compounding continuously, we're using the above formula. So see if you can put a formula together given that we have $1,000 that we're going to invest at 5% interest. So for your interest, right, we have your $1,000 being invested. We have your rate as 5%. So if we were to put it into a decimal, we're going to move your decimal places 2 over to the left. So 0.05 is the value that we're going to be using. So we have A of T is equal to $1,000. E is the same, 0.05, and then T. We don't know what T is yet. We will perhaps have a question later where it tells us what type of T that we want to use. Then it says, how much will be in the account after 6 years? So this is where it gets to say, hey, when T is equal to 6, what is in your account? What is A of T? So we can say, okay, well, if we are evaluating when T is 6, we can use your formula that we have over here and go ahead and put in 6 for T and see how much is roughly in your account. So let's go over here. I'm just going to clear everything out. So you have $1,000. We have E raised to the 0.05, I believe. Yep, that was 0.05 times your 6 years. So we have 1,349 and 86 cents or so. Oops, I already forgot what it was. 149. So that is in your account after 6 years. So let's say after the 6-year mark, at what rate will your account be growing? And you'll notice that it's saying, hey, at what rate? Keep in mind, each time we see rate, that is just saying to derive. And we want to derive specifically when t is equal to 6. So now keep in mind what you have learned about the derivative of a from our previous lectures. We said this is really k times, in our case, a t, where k is the amount, is your rate. So that would be 0.05. So for us, we have 0.05 times a of t, and that is your amount, or that is your equation that we had been using. And now we want to know specifically for 6 years. So I'm going to do that exact same formula, but now use 6 years. And notice that I'm not bothering with adjusting or simplifying here. I am just going to take my initial value, which this is your value in the account right here, and we're just going to be multiplying that by 0.5 or 0.05. So in my Desmos here, I'm going to take this value here and just multiply it by your rate. That is because your chain rule, that's how it's going to be working. So we have 67.50 cents or so. So this is roughly 67, and we'll just say 49 cents because I believe there wasn't anything really after the 9. So this is, so your account after 6 years is growing by $67.49 per year. Then it says, how long is required for the initial investment to double? So if we know that your initial investment is $1,000, and to double that, right, to double it is really just $2,000. And we want to know, what is t? How long will that happen? Right? So if we know that we have P of t on that side, we also know that P of t, actually even better, I also know that the derivative of P of t, actually, I'm so sorry, not that derivative. If we know that P of t is equal to 1,000 e to the 0.05 t, that these are equivalent structures. So we can just put it over here and then use your skills from chapter 4 to solve for t. We don't know what t is. So see if you can pause it here if you haven't done so already. So let's go ahead and divide by 1,000. So you're left with 2 is equal to e to the 0.05 t. To get rid of e, we have to write in an ln, or you can swoop, but that'll cancel this and allow your 0.05 to drop. So we have ln of 2 is equal to 0.05 t. So t is equal to ln of 2 over 0.05, which is roughly 13.86. 13.86. So from a time perspective of it, we have completed 13 years and we're well into our 14th year. So really this is about 14 years. So it'll take us about 14 years for our initial investment of $1,000 to double into $2,000. Now let's have you guys try example 2, where it says Pablo Picasso's The Dream was purchased in 1941 for a war distress price of $7,000. The painting was sold in 1997 for $4.8 million, the second highest price ever paid for a Picasso painting at auction. What rate of interest compounded continuously did the investment earn? So we want to know not so much the rate as in the derivative, but more so the rate of your interest rate. So this is just referring to the interest rate R. So let's see what we have been told. So one thing is that we can say, okay, for the year 1941, it was initially purchased. So we're going to use the time frame 0 here. This is 0 in year 0. This is when it was first purchased, was worth $7,000. But in 1997, which however many years after, right? The difference between 1941 to 1997 is about 56 years. So 56 years later, it was then sold as $48.4 million. So we can do one of two things, either make this into millions or make this into like expand your million. So it's up to you if you want. I would probably put, I don't know, I'm not a huge fan of writing out all of these zeros. So I would say this is by moving it over. So 6, we have your decimal over here, which actually, let me show that. We're going to move it 1, 2, 3, 4, 5, 6 for your millions. Oops. Let me try that one more time. 1, 2, 3, 4, 5, 6. So this is your new decimal place. So this is in millions. So now we can go ahead and start to build an equation. So P of T is equal to your initial value, that being, and we're just going to put it into millions. So we have that, e to the RT. We don't know your R yet. That is something that we need to figure out. So that is R here. We also know that this is in dollars. This is P of T. This is P naught. So we know that this is 48.4. And again, this is in millions over on this side. And we know that T, your time frame, the difference between these two is 56 years. So this is how we can go about solving for your rate. So first thing to do is to divide e to the 56r. Then we can take your natural log on both sides. So this part is very, very repetitive. The only new thing is that we are now giving it a different sort of context with like a business mindset. So R is equal to ln of 48.4 over 0.007 divided by 56. Let's go ahead and type that in. So we said we have ln of 48.4 divided by 0.007, close that parentheses, divided by 56, and we have 0.1579 or so. 0.15, oh, 0.1579. So keep in mind, if we're talking about a rate, we want to put it into a percentage. So we get to move your decimal place over. So it's about 15.8% interest. So that is if we compounded it continuously the investment that it would have earned at this particular rate. Now that is just if we have a continuous compounding. However, we can compound over various amounts of time. So we know that A of t is your amount. We know that P of t is your initial amount. Then when it comes to compounding over a specific amount of times in a year, we can say 1 plus your rate over m. This is your compounding period, raised to m times t. So really the only new thing is this m here, is that this is your compounding period. So, and this is always over some sort of a yearly context. So if we say, hey, we have annually. Annually means that it's only happening one time in the year. Monthly. How many months are there in a yearly context? Well, there's 12 months in a year. What about daily? Daily, there are 365 days in a year. And weekly, there are 52 weeks in the year. If we said semi-annually, well, that is 2 times out of the year. And another one, quarterly, there are 4 quarters in a year. That is if you kind of break them up into 3-month segments. So those are your more common ones. Of course, you can do bi-weekly or bi-quarterly. I guess that could be another one, but there's a lot of them out there if you wanted to. But those are kind of the bigger or the more common ones. This is in a yearly context. So compounding period. So this is what your M would equal. So let's take a look at your quick example. So it says, if $1,000 is invested at T% interest for 1 year, and that is interest is compounded once a year, quarterly, monthly, continuously, which results in a higher final value. So if we know that your A of T, right, is your initial investment of $1,000, and we now have some sort of a compounding period. This is annually, where we have annually, right? We have your rate 0.06, 1, 2. So rate is 0.06 over, and then R's being annually, right? What would we use for M? Well, we said annually in the context of a year is just once a year. Then we have M times T, so that would be 1 times your T is equal to 1. So for us, we have 1,000, 1 plus 0.06 to the first power. And I'm just going to copy and paste this. And let's do it again for quarterly. I'll come up with what they all equal here in a moment. So we have quarterly, that'll change your output just ever so slightly. I'm going to copy this. There we go. One more time. Quarterly, so how many quarters are there in a year? Well, there are 4 equal quarters in a year. You'll notice I'm not going to bother simplifying there. Monthly, there are 12 months in the year. And continuously, well, this one would have your different formula. This is the one where we have your E, where we have 1,000 E to your rate, 0.06 to your context of time, 1. So let's go ahead and plug these in and see what values we get. I'm going to clear all of these out. So we get $1,000, 1 plus 0.06 divided by, and I'm just going to do the 1 over here, raised to the 1 times 1. So you get $1,060. I wonder if I can copy and paste here. Nope, 1,060. We also have, really, I can't. Nope. We can change this to 4. So we have 1,061 or so. So I'm going to write some of those down. This is 1,060. This is roughly 1,061 and 36 cents or so. We also have monthly, or we're just going to change that to months. Change this to months. So 1,061 and 68 cents. So far it looks like monthly is in the lead, and then let's try it with continuously. $1,000 e to the 0.06 times 1. So we have, oh, a lot bigger. Hold on, 1,000. Oh, there we go. Let's do point. There we go. 1,061 and 84 cents. So overall, which investment is the best investment? Well, that would be your continuous. Now there is a very quick extra example. Let's see what you make of it. It says, find the present value of $2,000 to be received in 12 years if the money may be invested 8% compounded continuously. So if we know, if we do not have your present value, right? Present value is P naught. So we don't have P naught. That's something that we need to find. We do have your final amount though, as 2,000. So it says $2,000 to be received in 12 years. So that 12 years period hasn't come up yet, right? We want to know over that whole duration, what is at the end. We also have your rate at 8%, and we are compounding continuously. So keep in mind what we know about compounding continuously. This is P naught e to the RT. So we have $2,000 is equal to P naught e to the 0.08, and your t is 12. So we can go ahead and pretty much, if we are just trying to solve for P naught here, we can divide everything over to the other side. So we should have $1,000, $2,000 divided by e to the 0.08 times 12, because this is some sort of numerical value and we're trying to solve for P here. You'll notice that I am not rounding yet. So when I go to put that in over here, we have $2,000 divided by E being raised to the 0.08 times 12. So you have $765 and let's say 79 cents. So P naught is roughly $765 and $79. And you'll notice that you always kind of want to make sure that some of your answers are going to make sense. If you had gotten a number that is bigger than your end investment, we know that is going to be a very big issue. So you always want to kind of retrace your steps and make sure that it makes sense. All right. And last thing, if we are talking about some sort of exponential decay, that is just as far as your interest rate goes. It is just going to be using a negative interest rate. This happens when banks want to encourage customers to invest in their savings rather than any sort of short term deposit. So it is possible to have negative, excuse me, interest rates.